Hi scholars, let's write a proof about the convergence of a quadratic function. To start, let's recall the key definition we will use. We say a point y is the limit of a function f as x approaches z, provided for all epsilon greater than 0, there is a delta greater than 0, such that if 0 is less than the absolute value of x minus z, and that is less than or equal to delta, then the absolute value of f of x minus y is less than or equal to epsilon. When this is the case, we use the show notation, where we have the arrow from x to z under the lim and follow this by f of x, and we write that this limit equals y. When we go to make a proof by directly applying the definition we just talked about, we can often use similar steps, which I'll outline here. First, in my proofs, I like to state the definition of what I must show. In this case, that usually looks something like stating, let epsilon greater than 0 be given. It suffices to show there is delta greater than 0, such that if 0 is less than the absolute value of x minus z is less than or equal to delta, then the absolute value of f of x minus y is less than or equal to epsilon. Stating this establishes our goalpost, by which I mean we make explicit what it is that we aim to do in our proof. Next, typically I will do some scratch work for finding an upper bound for the absolute value of f of x minus y, that is typically some number, say m, multiplied by the absolute value of x minus z. The reason I want to do this is given in the next step, where I can pick delta to equal epsilon over m to make the desired statement hold. Then I conclude my proof with some observation that combines the results in my found inequalities to directly be able to state the desired statement holds and complete the proof. Before writing any formal proof, let's try and reason about the problem graphically. So let's plot our quadratic function. Here we'll focus on the quadratic function x squared over 2 minus x plus 1. Let's also consider the limit as x approaches 2, which is where the quadratic function equals 1. For the proof, let's assume we are given a small positive epsilon that acts as a bound on our function values. We shade the region for this range of values in white, going from 1 minus epsilon to 1 plus epsilon. Now, I want to use straight line approximations to bound my function from above and below around x equals 2. This is where step 2 in the outline comes in. At the top here, we see the absolute value of our function minus the limiting value is equal to the absolute value of x over 2 times the absolute value of x minus 2. This is close to the form we want, and we know we are taking the limit as x approaches 2. So we know that the absolute value of x should be near 2. If we go ahead and pick a bound of 1 on delta, then we can know for sure that the absolute value of x is less than or equal to 3, and so we bound our discrepancy between the function value and the limit by 3/2 times the absolute value of x minus 2. We include the restriction on x values by writing that the absolute value of x minus 2 is less than or equal to 1, and the implies arrow before the string of inequalities. What this bound means graphically is that for sufficiently close x to 2, the yellow quadratic curve is between the orange lines I just added in. This is great because now we can identify where the orange lines intersect with the lower bound 1 minus epsilon and the upper bound 1 plus epsilon. I've added vertical dashed green lines for where this happens, and this tells us what delta should be. Letting 2 plus delta be the x value shown, we can set the 1 plus epsilon equal to 1 plus 3 delta over 2 and solve for delta to find out that this delta should be equal to 2 epsilon over 3. Now, we already assumed delta was less than 1, and so we can combine these two to get our value for delta. Sure enough, if we pick any x in the interval, say slightly to the right of 2, we find that the value of the quadratic function is indeed between 1 minus epsilon and 1 plus epsilon. So sweet. Now we can formalize this in a proof. We start the proof with step 1 from our outline, which is to state the definition of what we must show. So we write let epsilon greater than 0 be given. It suffices to show there is delta greater than 0 such that 0 less than the absolute value of x minus 2 less than or equal to delta implies the absolute value of x squared over 2 minus x plus 1 minus 1 is less than or equal to epsilon. Next, we'll define alpha to be the quantity shown based on what we saw in our diagram. Then we'll find an upper bound for whenever the absolute value of x minus 2 is less than or equal to alpha, by first rewriting this as the absolute value of x over 2 times the absolute value of x minus 2. Now, here's a sneaky trick. We want to bound everything in terms of the absolute value of x minus 2, so we can subtract and add 2 and then use the triangle inequality. Then, because alpha is less than or equal to 1, we can bound this leading fraction by 3/2. Now, I'll add a short explanation in words briefly describing why these inequalities hold. We need to bound the simplified expression by epsilon. First, we bound the absolute value of x minus 2 by alpha, and, by our choice, we know it is no more than 2 epsilon over 3. Multiplying these fractions gives us the desired epsilon. Like before, it's a good practice to include a brief summary of any parts that might not be immediately clear. So we'll write where the second inequality holds since alpha is less than or equal to 2 epsilon over 3. From our last two inequalities, we can now write the implication that the absolute value of x minus 2 less than or equal to alpha implies that the absolute value of x squared over 2 minus x plus 1 minus 1 is less than or equal to 3/2 times the absolute value of x minus 2, and that is less than or equal to epsilon. This is exactly what we wanted, which we can say formally by saying, thus the desired statement holds for delta equals alpha, and the proof is complete. That's all for now. If you enjoyed the video, please like and subscribe. Cheers!